I'm going to talk a bit more about source transformation, really just with the idea in mind of what we mean by terminal pair equivalence. So I'm going to keep harping on this because it's an important aspect of Thevenin equivalent circuits and just circuits in general. So just a reminder of what the source transformation is. It allows us to take a voltage source in series with a resistor and transform that to a current source in parallel with a resistor, or vice versa. And you may remember that the relationship between the elements in these circuits is that the resistance is the same and the current source is equal to the voltage source divided by R, or the voltage source is equal to the current source times R. So that's how we go back and forth. And the terminal pair equivalence, one way of looking at that, I've talked about this before, but one way of looking about that is anything that I put between terminals A and B will result in the same current and voltage from terminal A to terminal B. So if I put another resistor here and I put the same resistor here, then they'll draw the same current and they'll have the same voltage drop across them. And so that's how we prove things are terminal pair equivalents. But it has to be true for every load. So I could even put another circuit between A and B. That would just mean that the voltage into terminal, or the current into terminal A, and the voltage from terminal A to terminal B would have to be the same for both circuits in every case in order for them to be considered terminal pair equivalents. So one of the things we do, not so much in source transformation, but in this thought about terminal pair equivalents in general, is we look at two extremes. We look at what happens if we have an open circuit and what happens if we put a short circuit between A and B. If we have an open circuit, the current will be zero. So what we're really comparing is the voltage between A and B with the circuit on the left and the circuit on the right. If we short the terminals, the voltage from A to B will be zero, and so we're looking at what we refer to as the short circuit current. So I'm going to be using these expressions in the next section. So once again, we talked about this. I basically said just what you're reading here, that if the sources are turned off, the resistance at the terminals are both R. If the terminals are short-circuited, the current needs to be the same. If the terminals are left open-circuited, the voltage needs to be the same. Now, be a little bit careful with this statement right here, because this does not work if you have dependent sources, because obviously you can't turn dependent sources off. This is a continuing area of concern for me in this book. I believe they make some misleading, if not outright incorrect statements. So as we go through this set of lecture notes, I'm going to point these out, and I'm just going to tell you that this is kind of like node voltage. This is one of these areas where you really need to follow what I go over in the videos and in my examples, rather than trying to get this out of the textbook, because as I said, I think at best it is confusing and misleading, and at worst you could make a case that they're just flat out wrong. So now a dependent source, you can't use superposition with dependent sources. You can't turn dependent sources off, but you can do source transformation. The one thing to be very careful of in doing source transformation, remember this dependent source voltage, it'll transform into a dependent source current, but remember the variable that defines the dependent source needs to remain in the expression for the dependent current or voltage source. So that'll be an issue. Here are some source transformation rules that we've already been over, namely talking about the direction of the current source. As you do the transformation, it would be directed toward the positive terminal or in the same direction as the positive terminal of the voltage source. This stuff here is pretty obvious. Obviously, if we don't have a resistor present, we can't do a source transformation either direction. All right. So more on terminal pair equivalence. This just gives a definition that I like, that I have seen throughout my career in very good textbooks. So we can say two circuits are terminal pair equivalents if any load placed between the terminals results in the same current and voltage at the load. Two convenient choices to prove terminal pair equivalence are, first of all, look at the circuit under open circuit conditions. The voltages at the terminals are equal under open circuit conditions. The currents at the terminals must be equal under short circuit conditions. If those two conditions are true, then you can say the two circuits are terminal pair equivalents. If you don't have any dependent sources in the circuits, then you can say the equivalent resistance at the terminal pair will be the same. However, this doesn't apply with dependent sources because we can't kill dependent sources. So you have to be very careful with this, looking at resistances at the terminal pair. We're going to do it, but we're going to do it under very specific circumstances, and we're going to be sure we describe what those circumstances actually are. All right, so this gets us to Thevenin's theorem. First of all, let's talk a little bit about the justification for Thevenin's theorem. Typically in circuits, you have some kind of a linear circuit that is built basically to provide power or current and or voltage to a load, depending on what the load is. So maybe you have a motor and it requires a specific current, and so you've got to have a circuit that will provide that current, or maybe you've got something else that requires a specific voltage. You've got to provide that voltage. So the load out here is whatever you're actually trying to deliver some power to. We'll talk about it in terms of power. What Thevenin's theorem says is he says a linear two-terminal circuit. So that's what this is. Two terminals means coming out of whatever's in this box, you have a connection A and a connection B. Can be replaced with an equivalent voltage source and resistor. So this, whatever is in here, however complex it is, as long as it's linear, we can replace it with a single voltage source in series with a single resistor. The voltage source's value is equal to the open circuit voltage at the terminals. So you get the load out and you leave these terminals A, B open circuited, and that voltage is this Thevenin equivalent voltage. This is the statement that I was referring to that I think we need to be careful with. Okay, it says the resistance is equal to the resistance measured at the terminals when the independent sources are turned off. Notice his statement, independent sources. This is a weak definition. So yeah, it applies sort of, but in my opinion, it is a weak definition. A better general definition that works all the time. The resistance is equal to the open circuit voltage divided by the short circuit current. So we would take out this load. Instead of open circuit voltage, we would place a short. This current would be defined as the short circuit current because it's going to go right through this short. If we take the short circuit current, if we take the open circuit voltage, which is V Thevenin, and we divide it by the short circuit current, we'll get the Thevenin resistance. This works as long as you have at least one independent source present in the system. So we're going to show some examples on how to do that. We will show some examples on how to do this as well, but once again, we're going to limit ourselves to some specific cases where that works. So, Thevenin's theorem, there are two cases to consider when you're finding the equivalent resistance. One is if there are no dependent sources, you can find the resistance by turning off all the sources. So in other words, we're going to kill all the voltage and all the current sources, and we're going to look for the equivalent resistance at terminals A and B. If on exam 1 you had difficulty finding equivalent resistances, this is where that's going to come back to haunt you, and you need to be sure you really understand how to determine if resistors are in series and parallel and how to simplify those, because that's how we're going to find the Thevenin equivalent resistance in the case where we have no dependent sources. And the Thevenin voltage is found just by finding what the open circuit voltage is. That's usually most easily accomplished using the node voltage method. So if you didn't like node voltage method, Most of the time, it's going to be significantly easier to use than mesh current. Okay, this is what I do not like. So when you come, if you are reviewing things in the textbook or on the PowerPoint slides, I think this is like I said, I think this is a weak definition, and I think it's a weak methodology because they try and lump independent and dependent source circuits together. So I'm not going to do that. I'm going to do this. So what you're going to do is, first of all, if there are no dependent sources, you're going to do what we just talked about. If there are dependent sources, you're going to first find the open circuit voltage. This is the Thevenin equivalent. And then you're going to find the short circuit current. The Thevenin resistance is the open circuit voltage divided by the short circuit current. In my opinion, this is a much more straightforward way and approach to find Thevenin equivalent when you have dependent sources. And so that's the way we're going to do it in this class, and we're kind of going to ignore what the textbook says. So Thevenin's theorem basically is very powerful in circuit analysis because it allows you to simplify a circuit down to a single voltage source and a single resistance. And that's huge, particularly if you're looking at things like how much power is that circuit going to deliver to a load, which is one of the main applications of Thevenin's equivalent. So we're going to be able to see that we can basically take a big circuit, we can replace it by a single independent voltage source and a single resistor. There's a way to do this on multisim in order to check. The way you would do it on multisim is measure the open circuit voltage at a pair of terminals, and then you would put a short between the two terminals and ask multisim to find the current through that short. And so that basically is finding open circuit voltage and short circuit current. Right now, many of you are still struggling with the basic rules for solving circuits, but at some point, some of these problems you can certainly put into multisim and get it to simulate for you so that you can see at the very least whether or not you have the correct answer. Okay, there is another theorem called Norton's theorem, and it's similar to Thevenin's theorem, except instead of finding a voltage source in series, you're finding a current source in parallel. And of course, we know a voltage source in series can be transformed into a current source in parallel using source transformation, so this should be no surprise, but basically this is called Norton. The Norton resistance will be the same as the Thevenin resistance. The Norton current will be basically the equivalent circuit where a source transformation was done on Thevenin. Can you find the Norton current directly? Yes, you can. You can do that. You can do that from this circuit doing the same thing that we did in the past. So you would find the short circuit current between A and B, and that would actually be equal to the Norton current. And then you would find the equivalent resistance between A and B, either by finding the open circuit voltage here or by finding the equivalent resistance if there are independent sources only. So that's Norton's theorem, similar to Thevenin's theorem. So in the examples videos this week, we're just going to look at several cases of Thevenin and Norton. So here's basically they're illustrating what I just said, that you find the Norton current by finding the short circuit current between terminals A and B, and then you find the resistance in the way we just mentioned. Once again, they can be related to each other, looking at source transformation. So in some circuit arrangements, it is possibly easier to find the Norton equivalent circuit and then transform to Thevenin using source transformation, or vice versa. So this is a summary of what I said before. Basically, the Thevenin or Norton equivalent circuit requires that we find the open circuit voltage across terminals A and B, the short circuit current at terminals A and B. And then basically, I'm scratching this entire last statement because once you found the open circuit voltage and the short circuit current, the Thevenin equivalent resistance is just the open circuit voltage divided by the short circuit current. I think, yes, this reaches the end of what I want to cover in this video. But I do want to point out one thing. So Thevenin and Norton is dependent on where the terminals are located. So suppose, for example, you had a couple of other terminals that came out of here, maybe C and D. I won't try to, well, maybe I will. C and D. Okay, the Thevenin and or Norton equivalent circuit is not the same for A and B as it is for C and D, unless it's just some kind of fluke of geometry. So the Thevenin equivalent circuit is highly dependent on where you take your output. And if you move your terminals and take your output at a different location, then you're finding a different Thevenin equivalent. So I will say this is one of the biggest problems that I observe that students have in finding Thevenin equivalents, particularly when finding the open circuit voltage. They'll find a voltage that will be a different voltage somewhere else in the circuit, or they will try to simplify the circuit too much to find the voltage. So got to be very careful that you maintain these terminals. You don't want them to get absorbed in a source transformation or anything unusual that you would do to simplify the circuit. Otherwise, you've eliminated the terminals at which you're trying to find the Thevenin equivalent. And that's a problem, and it's a problem that I observe pretty often as far as common errors that people make on exams. Now that begs the question, is it possible to do enough source transformation and resistor simplification to get to this point? And the answer is yes, theoretically, especially if you're willing to do delta to Y and Y to delta transformations on your resistors and you have no dependent sources. Eventually, you could simplify your circuit to get either the Thevenin or the Norton. So let's go back and look at the... I'm just going to look at the page that has both circuits. I guess they don't have it. So here's the Thevenin. Theoretically, whatever's in this circuit, you could use enough source transformation and resistor combination and simplification and take enough steps, kind of like we did in some of the examples I showed in the lecture where we went over examples of source transformation. Theoretically, with independent sources only, you could eventually simplify this down to a single voltage source and a single resistor. However, if you have dependent sources in the problem, you can't do that. So that would be the first case where you couldn't do it. And the other thing is, it is extremely easy to make an error when doing multiple source transformation and resistor combinations. First of all, you have to be very good at recognizing what's in series and what's in parallel. You have to have some intuition about which source transformations to do and the order in which you do them. And if a circuit gets complicated at all, the number of steps becomes increasingly large. And you may end up to the point where you have to do Y to delta transforms on your resistors, and then that gets very complicated. And so if you're not really good at seeing the geometry of the circuits, my opinion is that is more trouble than it's worth, and you're better off just using node voltage or mesh current. So we will have some videos that accompany this that show some examples, but this sort of provides you with the overview and the theory behind Thevenin.